Hello everyone. We're going to be looking at 14.8, which is the Lagrange multipliers. And what the Lagrange multipliers are for is for, where's my little constraint? It's for finding the highest point or the lowest point, but given a constraint. And so we're looking here. So I have right here on my XY plane my constraint, and I'm saying, okay, what is the highest point? Ooh, I don't have my constraint showing. Sorry. I'm not going to redo it just because of that. So here's my constraint. And so what is the highest point that just above my little orange constraint? What is the very highest point? What is the very lowest point? And we're going to be able to use a Lagrange multiplier to do that. Now, kind of the idea, do you guys remember about level curves, is that we can take from this here, our surface, and we can graph several level curves by letting our function equal different constants, and then we're taking it down a dimension. So this is in 3 dimensions. Those level curves are in 2 dimensions, and we can graph them in 2 dimensions. And our constraint, we can do the same thing with our constraint. And so kind of the idea, I'll show you here, paper view. So we're here on our paper view, looking at our paper for our Lagrange multipliers, is so the objective of them is to find the maximum and minimum values of an object function that lie on a constraint curve. And so kind of in the way that we're going to be thinking about this is that we could look at different level curves for our function that we're thinking about, and we can look at our the level curve that goes with our constraint function. Usually this is just one particular value, and the idea is that we're going to be looking where the two of these are the point where they meet just tangent to one another. Now, we don't have something that talks about our tangents to level curves, but I hope that you remember from yesterday that our gradient, remember what it gave us? Our gradient was a real special guy, and it gave us always the normal to the tangent at every single point, right? And so anyway, and so the idea is that, well, these both would have, the G would have a gradient and the F would have a gradient at this point. And when those normals are equal to one another, or scalar multiples of one another, means they're anyway. So that's kind of the idea of what we're going to be looking at. So the idea is the maximum or minimum values of the function that we're trying to find the max or the min of, the z value, how high it is, the very highest, the very lowest. They lie on this, our constraint are located both on the gradient of f and the gradient of g. And they're they're tangent, they're, no, not tangent, perpendicular, orthogonal, I couldn't get that word out, to the tangent vector of the level curve there. And so we'll be able to find these, and we're going to set them equal to one another, and they're going to be different just by a scalar because they'll be parallel to one another at that point. And the scalar that they use is lambda. And so I don't know, I kind of make it, to me it almost looks like a fancy H, but you'll see how I make them. You can see if you think that it's good. The method that we're going to use for finding it, it's not difficult, but it does get hard to solve sometimes. For both f and g, for f and g, both differentiable on the region R2 with the gradient not equal to 0, locate maximum or minimum values by taking these steps. Find lambda, x, and y that satisfy this condition, and also satisfy this condition, which is your constraint condition, you'll see. This is called your critical points. So you find those values are called your critical points. And then what you want to do is for each of these values that you find, you want to find, evaluate the function at that point. So how high is it at each of those critical points for each? and the largest one of those, so the largest z value is your maximum and the smallest is your minimum. And the same method can be extended if you're in 4 dimensions. So this is already in 3 dimensions, right? And the idea is when we use the level curves, we're projecting it down and getting it in 2 dimensions. So anyway, that's kind of our story on how we do that. So so what we're going to be, just to reiterate just real quick, we want to look where f and g's tangent vectors are the same. And so where they're just tangent, where they're just kissing each other, and that means that their normal vectors are the same. And the good news is, or scalar multiples of one another, and the good news is that we can find their normals because that is the gradient, and the gradient is made of the partial derivatives. And so anyway, so that's kind of the story. And so here we're going to go on an example. This is an example that is a picture. I'll throw that back there. And so this one is, so pictured are the contour map of f, and so this is made the, for different values of k, we've made the level curve drawing here. So at 10, when k is 10, when k is 20, when k is 30. And then they have this constraint function in here that, I'm sorry, on my screen is pink, but now is not any color at all. So I'm going to draw the constraint in here in purple just real quick. And because it's not on yours either, because it was photocopied in black and white, but on my screen it's better. Okay. And so what we're looking for is, where does it just kiss? Now I drew this and it made it go here. So you might be looking at this and saying, well, it just kisses so now in purple is G, which is our constraint. And you might be saying, well, it now just kisses there at 60, but it actually is just a little bit outside of that. So it would be at the level curve that's around 59 or 59 and a half. And so that's where our max is. Our max is around 59 or 59 and a half. And when I drew it with this wide pen, now it's looking at like 60 is what it's looking at. And our min value, so we're looking around, I'm sorry, I said that was our max value because I already knew that was our max value. I'm sorry. When we're going to find, that's a critical point. Something's happening there, and it's either the min or the max. And when I look, and I'm looking for where it just meets tangent. So here it crosses, and so I want to meet just where they just meet tangent, and that's somewhere there. And you know notice that that's on the level curve that goes with 30. And so because 30 is smaller than 60 or 59 and a half or 59, whatever you want to call that there, your book calls that 59 is what they called it. And so because they said I had to estimate. And so that is our min, is right there at 30. Okay. And then I have down here, so that we can go and look. So I'm going to change the screen here to my MacBook screen. And now we are looking at this situation. And it has it both as a 3D projection and also as a level curve. And what we have is our constraint, which is there in blue. And so our constraint is an oval. And that constraint is just going to stay there as one oval. So that 3x squared plus y squared equals 3 is our constraint. And you can see that when our constraint is projected up, onto our surface, that it's making, our surface is something that kind of looks like this. And that's kind of what it looks like. And then what we're going to be looking at is different values for our function. I don't think I get the option of turning that off, but for our function. And so this is a graph of our function, and we're going to be looking at different level curves of our function. And so I'll just let it animate and go through. And what we're trying to find is the point where the constraint, where it's the highest over that constraint. And what they've told us is the highest and the lowest can be found where your level curve for your function just kisses the constraint. And so, and that's where your tangent vector for your function and your level curve are the same. But more than that, it's where the normal is, because that's something that we can find, because the normals are both perpendicular to the tangent. So that's something we can find with the partial derivative, is it is perpendicular to the normal curve. So you can kind of see that as I try to just get here kissing, and we kind of look at, we'll get a good view on it. It doesn't look like it's at that maximum height. Oh, I got to go a little bit further to go. It really is. And I'm not very good at drawing getting the mouse here and getting a good level. There's a better shot of it so that you can see that it's just at the tip top where those are just kissing. And I think that they're not exactly lined up together, although I think they've done their best at that. So you can see that it's in that neighborhood, but it should be just perfectly. And I think that depending on your perspective where you have it angled, and then the minimum, and as long as you have a closed and bounded interval, continuous and all of that, we ought to be able to find a maximum and a minimum. Remember that theorem that we went, I got to go just a little bit more there and get a good angle on it so that you can see that that is hitting right at the lowest spot. And I've got this going crooked. Anyway, if you want to go on here and play around with it, you can definitely play around with it, but it kind of shows you, I like, because it shows you the 3D projection, and you can get rid of the 3D projection. They have another one in part B that's also asking you, and so we have our function, which this function, the way they've drawn it, kind of, and then this is the constraint. So this one's more, must be in four dimensions, but we can look at this in 3 dimensions. We can look at the contour map in 3 dimensions. And so you can kind of look at the same thing, when is it going to hit the tip top, and it's where those are, where the two are just kissing is the idea on it. Okay, so I am going to go off of this screen, back onto this screen, and back to my paper view, and I'm still working on learning how to do that better. Okay, so we did this page of our notes, and put that paper over there, and we're going to be now looking at our first example that we're going to do ourselves. So that's what we're going to be looking on now. And so this is example 2 that we're going to be doing ourselves. So our first thing is that what we want to look at is this part right here. Get my pencil going. Is our constraint. Oh, I got new lead, and so I'm making it work. And this is our function. And my friend Becky, she did a lovely job at drawing. This is our function. This is our constraint. Do you guys recognize what that is? It's an ellipse. And so if you wanted to just make a little quick drawing of that, you would divide here by 16, just so I can draw it down here. Trying to draw I'm not going to be able to draw the level curves of F. I'm not going to even spend time doing that, but I just want to show you where that constraint is, and then we're projecting that constraint up and then looking for the very highest point is what we're looking. So this is 4 over 4x squared over 16, just to get this ellipse in standard form so that I can just make a little bit of a sketch on it. So this is x squared over 4 plus, and this is y squared over 2 equals 1. And so this here, somewhere here between -1 and +1, is where x is 0. And then somewhere here between, right here at 0, I'm trying to draw it parallel to x, is where, parallel to the x I'm trying to draw it. So I've kind of drawn in there this is the floor in there, and I put an x there on the floor so that I have the 0 zeros there in the center. And I want to go in the x direction, I want to go 2. So on the x direction, I'm wanting to go from the center, I'm wanting to go 2 this way, and I'm wanting to go 2 this way. And in the y direction, I'm wanting to go the square root of 2, which is around 1.4. And so in this y direction, so here I'm wanting to go around 1.4 here somewhere, and this way around 1.4, just for the idea, not perfectly drawn, just for the idea. And so this is our constraint. And we are, lifting this constraint up, and then we're saying, where is that maximum point on here? So that's kind of our idea. And how we do this, the strategy for doing this, we have our function here, which was xy. And I have it where you can't see it, but I'm going to get used to that too. And so everything is a getting used to. And then we have our constraint function. And I want to write it like this: x squared plus 8y squared equals 16, like that. And what I'm going to be doing is I'm going to be looking just at that and saying this is a particular level curve of that function right there, the level curve when I have my constant at 16. And so that's what I'm going to be doing. So the things that I need, because the formula that they've told me to solve, if you remember, the formula they asked me to solve right here is that the gradient of f equals lambda times the gradient of g. So I have to find the gradient of f and the gradient of g. So that's what I'm going to do. And for order to find the gradient, you find the partial derivative. So this is fx here, and I'm getting y. Do you guys agree? And that's the partial of x. I say that wrong every time. Partial of y, which is equal to x. So the gradient right here of f is equal to yx. And then I want to do the same here for my g. So the gradient, the partial with respect to x on g, which is nice. These are not too bad, 8x. And we've had some that have been really bad, but this one isn't too bad, 16y. Okay. And then this is our partial, this is our gradient of g, which is 8x. Oh, that was an x. Didn't look like an x though, did it? And 16y. So hot diggity dog on that. Now what we're going to be doing is, remember, this is what we're trying to follow, that the gradient of f equals the lambda, and you can see how I make the little lambda. It's beautiful the way I make it. Everyone loves it the way I make it. Everybody thinks it's wonderful the way I make it. So I'm going to have my times my gradient of g. So when I multiply lambda in here, that's going to be, and you can write it in any order that you want. You can write 8x lambda and 16y lambda. And that's what I plan on doing. And so I'm going to have this idea. So I have yx here equals, and then over here I'm going to say 8x lambda and comma, and then I'm going to say 16y lambda, my choice on if I write the lambda first or if I write it before the x or after the x or whatever. It's all good. It's all good. And then by equating the components of my vector, so I have the x components of my vector and the y components of my vector, I'm going to get some equations that I need to solve. And I call them in algebra equation 1, equation 2, equation 3, because I'm just really, really, really clever like that. So I'm going to have y equals 8x lambda. That's equation 1. Equation 2, x equals 16y lambda. And equation 3 is your constraint. And in this case, my constraint was this one right here. 4x squared plus 8y squared equals 16. So that's my constraint. That's my equation 3. Oh, I'm writing it wrong though. And this is 3 equations, 3 unknowns. So I have 3 equations and I have 3 unknowns. My 3 unknowns are x, y, and lambda. And I don't really care about lambda too much. That's not what I want. I want x and y. But if finding lambda helps me find x and y, then I want to find it. And so they're all different, and they're hard to solve. I mean, as far as, and I told you, I got some of them that I was trying to solve that were 5 equations, 5 unknowns, and so it's coming. So anyway, so I'm looking at, well, what would be my best way of trying to solve this? And so the idea that I had for this particular one, after trying and thinking some other things, I hope I've given you enough time to think about what you would do, what would be your first step. This is a nonlinear system because you got x squared here and y squared there, and you got your x multiplied by your lambda. And so my thought on how to solve it was to take equation 1 and equation 2 and solve them both for lambda, and then see what I had. And sometimes I have to tell you that I've done things that didn't pan out, didn't help me out at all. And so, but this is something I found that does work good on this one. So remember, what I'm trying to do is I'm trying to find values for x, y, and lambda. I don't care as much about lambda, but x and y that solve all 3 of these for particular values of lambda are possible places where the max and the min are. And so that's kind of the idea. Okay, so if I do that, if I take equation 1 and I solve it for lambda, well, it would be y over 8x equals lambda. And if I take equation 2, so that was what I'm trying to solve, and this is my method of doing it. There are all different methods, and if you thought of something different, well, it might even work slicker than what I've got going here. And if it does, I've turned off the comments, so you can't tell me but you can tell me in class. I would be happy to hear it. So then my idea after that was that, well, they're both equal to lambda, so they must be equal to one another. And so then I got y over 8x equals x over 16y, 16y. And then what I did next is I thought, oh, well, now I have a great idea. I'll cross multiply and solve it. Now, one thing that I want to make sure of that everyone realizes is that if lambda was 0, just for a second before we go on here and start cross multiplying, because we have things in the denominator and we want to be kind of careful a little bit here. But if lambda was 0, do you guys agree that that would tell us that if lambda was 0, maybe I'll even write that out right here just so that you know that I thought about it. If lambda is 0, which is a possibility, then this equation 1 would tell us that y is 0. And this equation 2 would tell us, if lambda was 0, it would tell us what is 0. Yeah, I hope you're shouting at your computer screen, x is 0, right? And if you plug in x is 0 and y is 0 into equation 3, remember, these values have to solve all of them, then you get a contradiction. And so that is not a possibility for lambda to be 0. So lambda has to be non-zero. And I started worrying about that when, because I didn't want, hey, are things going to become undefined, or when am I going to get something weird? So lambda shouldn't be 0, because when lambda is 0, that leads to y is 0, it leads to x is 0, and that leads to a contradiction in equation 3 is where the contradiction lies. So every time that we find something, we're going to make sure that it doesn't make a contradiction in any of them. Okay, so no, don't want to think about that, right? And so now I'm on letting them be equal to one another because they're both equal to lambda. This pencil, I just put new lead in it and it's already going up and down. I hate that. It drives me crazy. I hate mechanical pencils that way. So now my idea was to cross multiply that. So when I cross multiply that, I get 16y squared equals 8x squared. And remember, I'm going to use all of my pieces. And right now I'm using equation 1 and equation 2. I'm hoping also to use equation 3. And so I'm hoping that that you notice that, well, even what the heck, look, I got 4x squared here. I didn't notice this when I did it before. I did it a little bit harder. But I could make this into 4x squared too. And same over here. This is 16y squared. I could make that into 8y squared. And why I want to do that is then I can substitute. What I did was I solved for either x squared or y squared, and then I plugged it in. But now I just realized that, hey, you know, you can get the whole, Donna, you can get the whole piece here if you wanted. So I'm just going to divide by 2. So if you're saying, yeah, but you could have divided by 8, yeah, I get that. But the reason I'm going to divide by 2 is it's going to get me 8y squared equals 4x squared. And what I'm going to do next is I'm going to plug this into equation 3. So this information is going to go into equation 3. So I'm either going to be substituting 8y squared with 4x squared, or vice versa, since they just coincidentally happen to be equal. I don't know how big of a coincidence it is, but it's the story. So right here, I don't know. I would prefer to have x's for whatever reason, which seems kind of crazy right now, but 4x squared plus, and then instead of right here, instead of 8y squared, I'm going to write what 8y squared is equal to according to this blend of equation 1 and equation 2. So which is 4x squared. And then that equals 16. So this has equation, this is equation 3. And all I've done is this little bit of substitution, right? Is that I've just come here and I've plugged in 8y squared is equal to 4x squared, and I've just substituted that in, right? And then boom, this gives me something I can solve, and I'll be able to find x. And so I'm like, oh my gosh, I'm so grateful, because solving 3 equations, 3 unknowns can be really, really hard. I don't care about knowing lambda. I only care about knowing x and y. And so I could actually find lambda if I wanted. And sometimes it's necessary to. So here, solving this is 8x squared equals 16, or that x squared equals 2, right? And long story short, values that are good are x equals plus or minus square root of 2. Okay, and now we want to find y values that go with them. So that's the next thing that I would like to do, is find y values that go with them. And so thinking about this, right, back into equation 3 I go. So back to equation 3, equation 3, the original equation 3 right up here, right? 4x squared plus 8y squared equals 16. But I now know that x is either positive square root of 2 or negative square root of 2. And because this is squared right here, because it's squared, it doesn't matter which one I put in. I'm going to get the same value. So sometimes when it's like that, I put the plus or minus in to tell myself that it doesn't matter, right? So if I put in positive square root of 2 and I square it, I get 2. If I put in negative square root of 2 and I square it, I still get 2. So when the dust clears here, this is 4 times 2, no matter if it was plus square root of 2 or minus square root of 2. So I'm using what I just found here about x in this equation. And so this becomes 8 plus 8y squared equals 16. And I want to solve that for y squared. And then I'll be like, hot diggity dog. And so I'm trying not to say that. I'm sorry. I'll be like, lovely is what I'll be like. And so something like that would be good. I don't know if that sounds good or not. I'll have to think. Y squared, right, equals 1. And that tells us that y equals plus or minus 1. Okay, so we did a nice job on that. It wasn't so bad at all. And I want to think, are there any other possibilities that I could have. So I thought this was if lambda was any number other than 0, that I could set them equal to one another and come up with. So whatever that number for lambda was, I think I have found it, and I used my third equation. So I think I have all of my critical points. There are actually 4 ordered pairs here. Would you guys agree? There's when x is square root of 2 and y is 1. When x is square root of 2 and y is negative 1. When x is negative square root of 2 and y is 1. And when x is negative square root of 2 and y is negative 1. I hope I said them all. And so we have these 2 conditions. So now what we're going to do is we're going to plug those things in. And so that's our next thing, is to test them. And so we want to know f of, and I always like to make sure I have, this is x comma y equals xy. And I don't use the plus and minus in there unless I have something raised to the square or raised to the 4th, because otherwise it's not gonna be the same for plus as it is for minus. So I'm gonna have my 4 conditions. I'm gonna have square root of x, positive here, and 1. And so I'm going positive, positive. And when I do that, when you multiply those together, you get the square root of 2. And can you guys see that if I make them both be negative at the same time, I also get the square root of 2? So I'm going to write that next, just so I can have a grouping of these that are both the square root of 2. And then the other 2 critical points I have are when they're 1 negative and 1 positive. So the square root of 2 negative and 1 positive would make negative square root of 2 when you multiply them. And the other way around, when the square root of 2 and then negative 1. Oh, wait, I didn't put the negatives there. I'm so tired. I'm so hungry too. And so that's both negatives right there. I think I said that. If I didn't say that, I'm sorry. It's like I have the same one going here twice. Both negatives, so that when I multiply them together, I get a positive square root of 2. That's what I was trying to do. I didn't quite manage it. Whoops. And so here we're going to get negative square root of 2. And so it's possible to have 2 maximum points. And so these are the 2 maximum points. And it's also possible to have 2 minimum points. So I have, these are my maximums, maximum point here. And this is my minimum point here on this constraint. And so as constrained by this little section right here. So just on that little section, these are my maximum point and my minimum point. If you're asking, are they absolute max and absolute min? And the answer is yes, that's what they are. And they just call it max in your book. And so they don't say local max, local min, unless it's just in that section. And so if you're like, well, what is the difference between the local max and the local min? And so this thing that I have right here, I hope that all these sections are not exactly the same height, but this one right here is a local max, and this one right here is just a little bit smaller than it, a little bit less high than this one is here, and this is also a local max. It's just the max in this little area, whereas whichever one of these is the very highest, the very, very largest value of z, that one, and so when I look on the side here, you can see that this one is a little bit higher than that one. That one is the absolute max. There doesn't have to be just one absolute max. There can be more than one, but it's only if they tie, right? And so, okay, we did a lovely job on that. Not too bad. It was pretty good. We laughed, we cried, we thought it was great. Okay, so now we're looking at this one, example 3. Find the maximum and minimums on, and then we have this, and subject to this. And so, and the lovely picture of it drawn out here. And so this guy right here is another ellipse. And so you can imagine ellipse down here in the bottom. I'm not going to draw it. I could though, if you were thinking, can you draw it? Yeah, I can, right? When you have this, I don't know if you guys remember about drawing those, you have to write this as x squared over 1/2 is what you have to do. And so that we're going to go to the left and to the right, the square root of 1/2. Well, this one's nice because I got 1 on one side, so that's why it's kind of nice. And so I can definitely, so it's not going to be a very big ellipse down there. The square root of 1/2 on each side, I don't know, here I am drawing it after I said I wouldn't. So there, and then 0, I'm trying to draw it parallel. I got a ruler. I got a ruler. So I can come in here, and there's the center right there, my awkward shape. And I want to go in the x direction, the square root. So I got my calculator going. I get my calculator underneath here. The square root of 1/2. 0.5 is 1/2. And that's square root of 2 over 2. So to the left and to the right, 0.7. So going to the left and to the right, 0.7 on my x-axis this way, 0.7, 0.7, and on the other is y squared over 1. It's almost the same. Almost is going to look like a circle because 0.7 and 1 are not very different. And so there is my constraint. Okay, so what we're going to do here is we need to find, this is like a level curve here. And so that's what we're going to find our gradient on. And this one was, what was it, 4x to the third minus or plus y squared. So find your partials. So that's what you want to do. You want to label your stuff because, man, there's a lot of steps and there's a lot of possibilities for making an error. And so if you just have things unlabeled, people don't know what you're doing, what you have. They don't know what you're doing. You're always, if you're going to be an engineer, then you're going to be sharing your work with other engineers. That's going to be what's going to happen. And so you always need to be showing them, other people that you're working with, what you're doing and what you were thinking so that they can overview your work. And if you just have chicken scratch everywhere, they can't follow that. And so it's good practice, in other words. And this is, this pencil is going to make me scream out. I guess there was just one more piece of broken lead in there, and I put new lead in, and I thought that that was a piece of new lead that was doing that, and it's not. So I'm gonna be done with my screaming out. Okay, so that's 2y. Hopefully I didn't make a mistake because I was talking. And so the partial of x, the partial of y. Now we're doing that for the g function. So we're having 4x. Couldn't be nicer on the partial derivatives here. And so I don't have to have all these concerns. So I'm having, remember, delta f, that's a gradient, del f, not delta, del f equals lambda times del g, which is the gradient of g. And our gradient for f is 12x squared, 2y. And over here, I'm going to be multiplying through by lambda. Your choice on, do you write 4x lambda? That's what I do, but you do you. And 2y lambda. And then to get my equations, I'm gonna get my equations by equating the coefficients. I haven't showed you the one that's 5 equations, 5 unknowns yet. It's coming. It's over here. And so, okay. So here we go. This is going to be equation 1. I like to name it equation 1 because that's what I do in my algebra class. 12x squared equals 4x lambda. And equation 2 equals 2y equals to y lambda. And equation 3, which is my constraint equation, which is this one right here, equals 1. Okay, so now I'm trying to solve that system of equations. It's 3 equations, 3 unknowns. I don't really care about knowing lambda, but if knowing lambda helps me, then I'm willing to know lambda. And so kind of the idea, I look at that and I realize, ooh, do you realize too, equation 1 only has x in it. And that's like, oh my gosh, how lucky is that? And so equation 1, EQ1, 12x squared minus 4x lambda, right, equals 0. And I can solve that equation by factoring. And so I can factor out a 4x here, and that gives me 3x minus lambda equals 0. And so setting the pieces equal to 0, I get x is equal to 0. The outside 4x equals 0, so x is 0. Or 3x minus lambda equals 0. And so that tells me that 3x equals lambda. And we'll see about that. Okay, and so then equation 2, well, equation 2 only has y in it. So I'm like, okay, equation 2 only has y in it. How can I be so lucky? And so I can solve for some y here too. So equation 2, 2y minus 2y lambda equals 0. I'm on top of my function, my picture there. Factoring out a 2y gives me 1 minus lambda equals 0, so that either y is 0 or 1 minus lambda is equal to 0, which means that lambda is equal to 1. Is that okay? And that's or. This is true or that is true. You have to make something that's true for all 3 of them, and there could be more than one thing that is true, but y doesn't have to be 0 and lambda 1 at the same time. And so anyway, okay, so here is my idea, is that I'm going to use all of these things that I just found that can happen for me. And I'm going to say if x is 0, just because it's the first one here listed, and I'm going to be putting this into equation 3. So if x is 0, and then into equation 3 I'm going to go. So I kind of put these 2 equations together and I came up with something. And into equation 3 I go with x is 0. So 2 times 0 squared plus y squared equals 1. So there's equation 3 right there. And I've just put in x is 0. So that gives me y squared equals 1. So that tells me that y is plus or minus 1. And so that's something that ought to satisfy all 3 of the my situations here. And so this is giving me the point f at 0. You could just write it as 0, an ordered pair, or you could put it as f 0 and then plus or minus 1. Okay. And I'm going to be checking these things out. So I'm going to make a little line. I found that one. And then I didn't know what to make of that. And so I skipped it and went on to y is 0. I was thinking, well, that's not very helpful to me. And so when y is 0, so if y is 0, into equation 2, so into equation 3 again, so into equation 3, we're wanting to go into equation 3 because that's my constraint equation. Then I'm getting 2x squared plus 0 squared equals 1. And when I solve that, I get x squared equals half, which means that x equals plus or minus the square root of half. And I'm more comfortable writing, because my calculator does it, right? Well, I had it on the screen actually from the last time that I did it. I had just done it just a few minutes ago. Square root of half, right? It's 2 square roots of 2. So I'm more comfortable writing that as 2 square roots of 2 because that's just how I was trained. And I know that they don't always rationalize the denominator in the book, and I consider it a sin. And so anyway, so this gives me the point plus or minus the square root of 2 over 2, comma, 0. Okay. And then lambda being 1, because I have that here. Remember, I didn't know what to make of the other. So if lambda is 1, how can I use that? And then I realized, oh, well, right here, we have that lambda equals 3x. So I can use this with equation, kind of with my equation 1 result there, right? That 3x equals 1, because that equaled lambda, which would then imply that x equals 1/3. And so now I'm going to go into equation 3 again, right? Always into equation 3. I have this new view because Mr. Lewis thought that you guys would like, if there was that view, I don't know, you'll have to tell me in class what you think of it, but it's making me a little self-conscious. And so, you know, I feel like, are my facial expressions, when I make crazy facial expressions, are they like Shohei Ohtani? Because I don't know if you've ever watched him play, but he makes the craziest facial expressions. Oh, I love it. So cute. Anyway, okay, 1/3. Stop talking about Shohei Ohtani. So equation 3, the angels are all done, and it's sad, sad, sad. Well, when you're watching this video, maybe they're not done. That's happy. That's a happy thought. So I plug that in there into equation equation 3, and when I do the math there, so 2 times 1/3 squared, so 2 times 1/3 squared, it's 2/9, right? So I have that here on this side, 2/9, and I want to take 1 away from it. So I want to do 1 minus that answer, which I had, which was 2/9 squared, which is 7/9. So I have here y squared equals 7/9. Oh, hi friends. I'm on my video. So hello, hello. Oh, you guys look so cute. Oh my gosh.
Did she show you did he show you the picture that I'm supposed to?
Oh yeah, I'm gonna text it to her.
Okay, yeah, definitely. Oh my gosh. Okay, Kev, I don't know if you'll win, but she will. Oh my gosh. They're going out to a Halloween party, and so, oh my gosh, it looks so cute. Okay, so y squared, sorry to stop the video for cuteness. So y equals plus or minus the square root of 7/9, which is plus or minus the square root of 7/3. Where'd the plus or minus go? Okay, so that works there in equation 3. This is when we had lambda is 1 and also satisfied this 3x equals lambda thing. And so now what we're going to do, so this gives that point, x was 1/3. I'm going to move my chart up here, 1/3. And then y was plus or minus square root of 7/3 is what that is. Now what we're wanting to do is that we're wanting to come up with what is the highest point and the lowest point is what we're wanting to come up with. So that's going to be kind of our goal. Now I want you to look back at our function for f. X is raised to the third. So that means that it matters if we use the plus or the minus because it's raised to the third. But y is raised to the second. So on the ones that are plus or minus, we just have to do it one time. Is that okay? So now I would like to, for my points, how many points is this? I don't even know. There's 2 points here. There's 2 more points here. And there are 2 points here. So that's 6 points, right? But I get to, because y squared, I get to treat this just like 1 point. They're going to be the same. And because x cubed, I'll have to do this at 2 different ones. And because y squared, I'll be able to do this in one swoop. And so that's kind of the idea. So I'm going to be finding here, this one was the one I could do in one swoop, right? And so I'm going to write my function down here, f 0 plus or minus 1. and then this equals, and this is 4, and then 0 to the third, right? And I don't know if I'll be writing my function for every one of these, plus, and then squared. And it doesn't matter if I write in here +1 or -1, it will be the same. And so for either one of those, it doesn't matter, right? This part's 0, so I'm going to get 1. And so for this, f at 0 plus or minus 1 is equal to 1. So that's it tight. And I'm looking at which one is going to be the tallest. Here I'm going to have to do it in two pieces. So f at square root of 2, comma 0. And yeah, I'm just going to put this in my calculator, friends, right? Why would I do this by hand over and over again? That's silly talk, silly talk, silly talk. So this is 4, right? And then it's supposed to be raised to, and then I'm going to have a fraction, square root of 2 over 2. I'm doing the positive one right now, as you well know. And then I'm going to end that parenthesis and raise that to the third. And then I want to add that with whatever my y value is squared, and my y value here is 0. So you would say, well, you didn't need to put that in your calculator, but yeah, I'm just going to kind of be editing my opinion here, right? I have here this function with x and y, and I know that I'm gotten on teaching algebra here and going at it too hard, but that's what I've got going on, and I'm just filling in the blanks because I've got that going inside the parentheses. And so anyway, okay, so here I am with this one, equals, getting my calculator, getting everything in the right spot. That's the square root of 2. And I'm just going to come in here and I'm going to edit because I wanted it to be negative as well. And I bet you already know. I hope you're shouting at your screen what it's going to be before I even figure it. So the negative, comma 0 is negative square root of 2, right? So I have these three so far that I'm looking at which one is the lowest, which one is the highest. And square root of 2 is around 1.4. And then I want to do this one here as well for this point. And so I'm kind of got these sectioned off here, f of 1/3. And then it doesn't matter because y is squared. I can do the plus or minus at the same time. They're going to be the same, so I don't have to worry. So I'm going to come in here and I'm going to put in 1/3 1/3, 1 divided by 3. I got lazy and didn't put the fraction key. If it bothers you, do the fraction key, right? 1/3. Either way, it doesn't matter. And then here, and then the square root of 7 in the numerator, and in the denominator 3. And I would get the same for the plus as I do for the minus because it's being squared, where I didn't on the cube. So this is 25 over 27, which is slightly smaller than 1. 27 over 27 is equal to 1. So I'm looking for the maximum, and I'm looking for the lowest, highest and the lowest, right? And actually, I get the highest and the lowest from this situation right here. So the max is, and in your book, they say a max of square root of 2 at the point square root of 2 over 2 comma 0. And I just write it as an ordered pair, and I'm fine with you doing that as an ordered pair. And I know that if someone told me, no, you can't write it like that anymore, that I could mock how they write it. But I think that I'm giving all the same information as what I think. I think I'm giving the point and what that high point or that low point is all in one fell swoop is what I think. So that's my story. So there's my answer there. I typically have on tests and labs, not always, but I try to have a place for you to put the max and put them in. And so I didn't on these worksheets here. I wish I would have. Maybe that's something I'll put in the future. And so if you don't have one of those, I said this already before, you should put none or not applicable or something to show that you just didn't leave it blank. Okay. last one that we're going to look at here. And I have a statement to make, and we'll do that problem. We'll do that problem later on a different time, but I'll just describe it so that you can kind of know what to do on it. So here they're asking us to find all maximum and minimums, but instead of being in 3 dimensions, it's in 4 dimensions, and they have so they have the x, y, and z, but the idea is going to be the same, and they have 2 constraints. And so being that they have 2 constraints, that's going to make, I'll show you how you put that together. So you call one of the constraints g, and you call the other constraint h, if you like. And so then you're going to do the gradient. This is like your formula. The gradient of f is going to equal lambda times the g constraint. That is the, I have the gradient going there. Did you see me not write the gradient? The gradient of g plus, and then another constant, and they use mu. And so I'm going to use mu as well, just like them. I think mu is spelled mu. And so they use mu is what they use, and I didn't choose it. And then the gradient of h. And so I'll kind of show you how we'll get this together. And so what we're going to have is 5 unknowns. We're going to have lambda, mu, and x, and y, and z. And so you're like, oh boy, oh, that'll be lovely. Will it fit on this piece of paper? Well, good news is that you can add a page 53 if you need to. I might have to run and get the paper from the other room or turn it over and use one of the backs. If I run out of room. I was able to fit it on my notes sheet, so maybe I'll be able to fit it on here as well. I don't know. Okay, so I'm going to let this one be my G1, and this, even though it doesn't have all of them, but this is G X, Y, Z, and this equals X minus Y equals 1. And then H, I'm going to let that one be H, my constraints. I call one of them H, call one of them G. It doesn't matter which one is which at all. No worries on that. So this is y squared minus z squared equals 1. Being they equal 1, I don't know if that's going to make it easier or harder, but anyway, that's nice. Okay, and then we're going to find all these partial derivatives. Now, do you guys agree with me? The partial derivatives are pretty easy, so would it be okay if I did them in my head? And just to save a little room, to save a little face here. And so the first one is the partial of x, right? So that's 2x, because the rest of these are 0 when you hold them as constants. So this is 2x. Do you agree that the next would be 2y and then 2z? And so easy enough that I hope that we didn't make a boo-boo on it. And then delta g, I think that it might be easy enough that we can do it without making a boo-boo too. So when you take the partial with respect to x, you get 1. That's not a very good vector. And then when you do with y, you get negative 1. And when you do with z, with respect to z, what do you get? Well, z is not there, so it's 0. And then for the gradient of h, we're going to get, for x, we're going to get, I almost said 2y, but I'm like, what? What? I guess I haven't had dinner yet. And so we're going to get 0 for the partial with respect to x. Then we're going to have 2y, and then negative 2z. And then when we put this together, and I kind of almost got the spacing right, that not on purpose, but it did turn out good. So I'm going to go ahead and use it, that this, right, and then this times lambda, oh no, I'm not going to be able to fit it. I'm not going to be able to make it work. It's going to be this, and then this times lambda, and this times mu, right? And so, and I'm going to then take the, equate the components, the x component, the y component, and so that's going to be the story on there. I think I better show my work there, because I'm wanting you guys to show your work, because if I don't know what you're trying to do, I don't give you partial credit. So if I mess it up, then I want you guys to give me partial credit. I'm going to multiply lambda through here, and so that is going to be, when I do that, that's going to be a lambda, negative lambda, and 0 times lambda is 0. And I want to multiply mu times through h. And so this is going to be times mu is 0, times mu is 2y mu, and minus 2z mu. I was going to make some mu jokes, but I think I'll better not, because this is so serious, it's not funny. And so here we have equation 1 that we're going to get by equating the x components. So I'm going to have 2x plus, equals, sorry, just checking you, equals lambda, plus 0. That's equation 1. Equation 2 is 2y equals negative lambda plus 2y mu. And equation 3 is 2z. I like to name them. You don't have to name them. And then 0 here, which is nice. And then minus 2z mu. And then equation 4, I like to name them because then I refer to them when I'm solving it so that I can see what I did later. If I've made a mistake or whatever have you, I could say, oh, well, what was I trying to use? Equation 5 or whatever have you. That's the reason I name them, is for me, not maybe necessarily for anybody other than myself. Okay, so equation 4 is x minus y equals 1. And equation 5 is y squared plus minus z squared equals 1. Okay, those are my two constraints. So you get all your mu's and your lambdas. I don't really care about mu and lambda, but if it helps me to find mu or lambda, then I will. And so why did I write plus 0 there? Does anyone know why I did that? Okay, I'm going to erase it. So looking at this and trying to see if there's any place that we kind of have a little bit of a foothold, that we can find anything, I can say that x equals lambda over 2, but is that going to be helpful? And then I maybe can plug it in some other places that x equals lambda over 2, but I don't actually see x any other places except for over here. And actually, if I could solve for y in terms of lambda only, that would be helpful. Or if I could solve for z, I can get it in terms of mu only, right? And actually, did you notice I can actually solve for z? Do you guys notice that? Because this would be 2z plus 2z. If you're thinking divide, this would be mu because I'm going to add that to the other side. If you're thinking divide by 2z, when you divide by the variable you're trying to solve for, you lose a solution. So dividing by the variable you're trying to solve for is not a good idea. You can divide by 2, and I could have divided by 2. I'm going to factor out a 2 right now, but I could have divided by 2 and that would have been okay. But dividing by z would have given me less solutions. And so that's not a good thing to do. I don't know if you guys remember that story, but I'm sure you do. And so I get, and the solution that I would be losing is z equals 0, which is a really, really good foothold for me. Also, I have 1 plus mu equals 0. This is or, and where mu equals then negative 1. And so that was really the only foothold I had on any of it. I might be able to use some of this information to help me with other things. So we'll give a C. So I'm going to be starting off here with z equals 0. So I'm going to draw a line here, and just here, if z equals 0, and I don't really care about knowing what lambda and mu are, and I care about knowing what, I want to know what x, y, and z are. So can you guys see that if I use equation 5 with z is 0, I can find y. And so, it seemed hopeless, right? But all of a sudden, I know a value that solves it. There might be more than one value that solves it, and but I know I know one of the solutions, and that is that z is 0, and so I can use that in equation 5. So here is equation 5. It's y squared minus 0 equals 1. So all of a sudden, I know that y is plus or minus 1. And so I know that when z is 0, y is plus or minus 1. And look, I have an equation that has x in it and y. And so when y is 1, I can solve this equation, x minus, and I'm going to let y be both things, 1 and also y equals negative 1, and 1 at a time. So, I'm going to write that right here. How did I do that before? I don't remember. So if y equals 1 in equation 4, x minus 1 equals 1, and x equals 2. So that gives me a complete set that z is 0, y is 1, and x is 2. So x is 2, y is 1, and z was 0. And I want to make sure that that solves both, that I haven't messed up, and it needs to solve both of my constraints. That's my concern, is does it solve both of my constraints. So here 2 minus 1 is 1, and here 1 squared minus 0 is 1. So yay. And then also y could be negative 1, right? So at the same spot, so if versus, I guess, on the other hand, y could have been negative 1. And when it was in equation 4, we get x minus negative 1 equals 1. So x plus 1 equals 1. And that tells us that x is 0. So this gives us the point x is 0, y is negative 1, and z is 0. So far I have 2 points, and I'm wondering, well, are there any other points that I might be able to get a hold of? And so the other point I might be able to get a hold of is when mu is equal to negative 1. I want to make sure that I don't get any contradictions, of course. And so I have these points, and I'm going to check them for how high they are. But I also had mu is negative 1. So if I start off along those lines, that mu is negative 1, then looking at what I have, when I say mu is negative 1, I can't put them in equation 4 or 5, right? But I might be able to use them in equation 2 or in equation, well, it doesn't help in equation 1 because equation 1 doesn't have mu in it. So it might help in equation 2. So let's try it in equation 2. So we're going to plug this into equation 2. So we get 2y equals negative lambda. And then when mu is negative 1, then this would be 2y, minus 2y. Is that okay? So mu is negative 1 multiplied by this gives negative 2y. So I just plugged in mu is negative 1 into equation 2. And I can add 2y to both sides of the equation. And when I do, I get 4y equals negative lambda. And what's wrong, Miss Susie? I don't know. What's wrong? Something's the matter with you. I don't know. Okay, and so now my thought is, and you know, whatever you want to think on this story right here, now I can, my idea was that I could get things in terms of, maybe in terms of x, was a little bit my idea. and then try to use it that way. And well, my idea was that I knew that this was lambda over here, right? And so that I can substitute in that lambda is 2x. So I get 4y equals negative 2x. So this was using equation 1. And the idea that I'm now on is now I have two equations, two unknowns with equation 4, right? Equation 4, I'll write it right here, is x minus y equals 1. And I can solve this either for x or for y and then plug in, substitute, or I can get them both in standard form and use two equations, two unknowns elimination method, whatever you have the heart to do. And so I solved for y. And so I divided by 4. You might say, no, that's the very worst thing you could have done. But that's what I did, and I got negative 1/2 x here. And then I plugged in to equation 4 that y is negative 1/2. So I got x minus, and then instead of y, negative 1/2 x equals 1. So that when the dust cleared, I got 3/2 x equals 1, because it's 1 plus a half, right, is 3/2. You can use your calculator if you need to. But I got the double negative, so it's a plus. 1 plus a half is 3/2. And then I divided by 3/2 or multiplied by 2/3, whatever you want to say, and I got x is 2/3. And I thought, hot diggity dog. So x is 2/3. And so then I needed to know what y is. And so then I found out using this equation 1 back over here again, or this spot here. Well, then y equals negative 1/2 times x. And all of this was led from mu equals negative 1, led me to finding these values for x and for y. And so here I'm getting negative 1/3. So I was thinking, okay, we know x, we know y, we need to know z. And so is there an equation that would give us z? And so I plugged into there. Oh, my brother's going on a walk. I'm telling him I'm coming because I'm almost done. Getting on shoes. I need a walk. Okay, so gotta hurry quick here. So here, when I plug this in here, equation 5, because then they'll send me a nasty text. You're not ready to go. And so this squared minus this squared, z squared, I'm trying to solve for z here. Z squared equals 1. And I'm plugging in that y is negative 1/3 right in there. And so when I square that, I get 1/9 minus z squared equals 1. When I take away 1/9 from both sides of the equation, I get negative z squared equals, do you guys believe me that 1 take away 1/9 is 8/9? Do you guys believe that? 1 minus 1/9 is equal to 8/9. And so I got negative z squared equals 8/9. And so that means that z squared equals negative 8/9, and that's not true. Z squared needs to be real. So all of this led to a contradiction. So we only have two critical points. Here's our two critical points. Remember what f looked like? It looked like square each point, right? That's what f looked like. And so we have for f, f at x 2, 1, 2, 1, 0, not x, y, z, 2, 1, 0. So I square this, I get 4. I square this, I get 1. I square that, I get 0. So this one is 5. And this one is, you guys are thinking, we'll have to always send text that our brother's going on a walk. Square, 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 we get 1, right? And so we have a max of 2, 1, 0 equals 5, and a min of 0, negative 1, 0 equals 1. There was one problem that I did that only came up with one critical value. It was a problem out of your book, and there may be one like that on the lab as well, and it only came up with one critical value. And so I was like, well, how do I know which one's the max and which one's the min when I only come up with one critical value on that? And I read about it, and because I hadn't seen it before, and I don't know that there was an example in the book, but there was a homework problem in the book that happened on. And what other people said was to pick another point and see if that other point is lower or higher than your point, and then you can tell which one it is, because that point is either the absolute min or the absolute max. So if you choose any other point, then you'll know whether it's low or if it's high. And that gave me the right answer. So I'm like, oh, okay, that's a good idea. And so I just wanted to mention that. Now I'm pushing stop and getting my shoes on and going for my walk out there with my family.